everyone, and welcome to our first video talking about limits. So this will be our limit introduction. Before we get to limits, let's just name a function here. F of x equals x minus 5 over x minus 5. And let's just analyze this function for a second. What do we know? Do we know what this is going to look like? I think with a little bit of manipulation, we do know what this looks like. X minus 5 over x minus 5, well, isn't x minus 5 divided by x minus 5 just 1? So are those equivalent statements? Almost. There is one thing that we did not take into consideration, and that is this x minus 5 in our denominator. And what that's telling us is that x cannot equal 5. And so yeah, this graph is going to look like f of x equals 1, except at x equals 5. At x equals 5, we're going to have a little gap. We're going to have a hole. So let's draw this out here. We have our f of x axis. We have our x-axis. Let's say this is 5 here. Let's say this is 1 here. And this is going to be a horizontal line until we get to 5. And then there's going to be a little gap there. Because at 5, our value is undefined. At 5, if I were to plug 5 into there, f of 5 is going to be 5 minus 5 over 5 minus 5, which is 0 over 0. And later we're going to call this something, we're going to call it an indeterminate form. So keep that in your mind. But right now, what we know is that that is undefined. So this is what our graph looks like. So if I asked you to find f of 5, you would say undefined. Say, I can't figure that out. That's undefined. I don't have enough information. Now, this is where the concept of limits comes into play, because there is a very clear pattern here. There's a very, very clear pattern here. Yes, there is a hole there. But if there wasn't a hole there, we could guess what that value would be. And so that is going to be our limit notation. So the limit as x approaches 5 of f of x. And what is that? So what we're asking is, as we approach 5 from the left and as we approach 5 from the right, what is the pattern of the graph? What is the pattern of the graph? Well, the pattern of the graph is that this is getting closer and closer. Well, it is 1. It is 1. Everywhere on this straight line, the value is 1. And we can get infinitely close. We can get infinitely close to 5. And it's still going to be 1. It's just at 5. It's undefined. And so because as we get infinitely closer and closer to the value of 5, the function is a 1, we would say that the limit of f of x is 1. Let's look at that on a calculator. Let's look at this numerically. So numerically would be looking at a table of values. So let's draw out a table before I take the calculator out. So in a table of values, what we'll do is we will center this table on 5, and this of course is x, and this is going to be f of x. And what we want to do is we want to get super close to 5. So maybe we have 5.0001, 5.001, 5.01. And then we'll go the other direction as well. So this would be 4.999, 4.99, and 4.9. Because we want to get really close. And you know what? If I added more zeros or if I added more nines, that would be closer and closer and closer. So let me see if I can use technology correctly here. So I'm going to put this for half the screen, and then I'm going to grab a graphing calculator, and I'm going to try to put that for half the screen. And we'll put our function in there, which is f of x equals x minus 5 over x minus 5. Now I want to change this into a table. So I clicked the gear. If you didn't see what I just did, I clicked this gear. And then I'm going to click the table option. And I can put these values in there. 4.9, 4.99, 4.999, 5. Okay, 5.0001. That was supposed to be a 1. 5.001, 5.01. So I'm trying to delete those parts of the table. I don't know how to delete them. So pretend like they don't exist there. But what we see as we make this numerical list of values is that the closer we get to 5, we are still at 1. And so if we wanted to fill in this pattern, if we wanted to ignore the algebra where it's undefined, then when we'd fill in this pattern, we would say, well, this has to be a 1, right? So this was 1, 1, 1, 1, 1, 1. Well, that would have to be 1. And so the limit here is 1. Let's try one that's a little bit trickier. Let's try one where we're on a curve. So let's call this one g of x instead, just so that we practice naming things. And g of x, let's say we are looking at the function x squared, except when x equals 3. So we are going to look at this entire function x squared except for when x equals 3. When x equals 3, we're saying that's outside of that x squared domain. And when x equals 3, let's say we have the point 2. So when x equals 3, we have the point 2. And of course, we could graph this. So this is going to be our g of x axis. This is going to be our x-axis. And we want to go up to at least 3. 1, 2, 3. 1, 2, 3. And that would have to make this at least 9. And let's pretend like that's somewhat accurate. So at 3, we know we're going to have a hole. And the value is 2. So now I'll draw my parabola. So there's my parabola. So what we know is we know that g of 2 equals 3. G of 2 equals 3. If I were to plug 2 into the function of g, I'm going to get, I said that wrong, g of 3 equals 2. I'm so sorry. G of 3 equals 2. We know that because if I were to plug 3 into the equation, I get 2. And that's defined right here. But what about the limit as x approaches 3 of g of x? What is the limit as x approaches 3 of g of x? And so what that means is, what is the curve? What is our curve doing as we get closer and closer to 3? From either side, what is the curve doing? So as I get closer and closer to 3, I am approaching this value. As I'm getting closer and closer to 3, I am approaching that value. And that value is 9. So to find the limit, it's not exactly what g of 3 equals. It is, what is the curve actually approaching? So let's look at this one. Let's look at this one. So g of x equals x squared, except for, let's see, I've never tried this before. Let's see, x, how do I say does not equal? Nope. Ooh, I bet there's a button down here. Move my picture. Okay, I don't know how to say x does not equal. So we're going to have to know that x can't equal that. So then as we're approaching, so let's change this to a table like we did last time. We want to be approaching x is 3. And so we want to get as close as we can to x is 3, 0.2.99999. And then 3.000001. We see that the value that we would guess would be 9. 9 would be right in between there. And so that is why the limit here is 9. So when you're finding limits, you're not exactly finding the value the function equals. You're finding the value that that curve is approaching, the value that would make sense to complete the curve.